In 9.1, we're going to introduce a lot of vocabulary. We're going to review angles, arcs, and also talk about different measurements with angles and arcs. So first of all, let's look at some terminology. Let's just say that you have a line and that line passes through, let's do 2 points, A and B. So between any 2 points, there's exactly one line. If I wanted to refer to this line and talk about it, I can just simply write line and use the 2 points AB. And that's what your book tends to do a lot. They use the word line. Order here doesn't matter. If I said line BA, it would still be the same line because it goes on infinitely in both directions. Another piece of notation you may see is just AB with a line over it, or BA, since order really doesn't matter. Typically, if possible, we write things in alphabetical order, but sometimes it's not possible. Now, if I didn't have a line that went on forever and I just had a segment of a line between 2 points A and B, then I could simply use the word segment and list the points AB or BA. The order here doesn't matter. Where A and B are what we call endpoints of our segment. So again, I could just write segment BA, be exactly the same. I could write AB with a segment over it. Order doesn't matter in this case, so I could write BA with a line segment over it. And the last one we're going to talk about as far as line segments would be our ray. So a ray has an initial or starting point, and then it's going to pass through another point. So it goes on infinitely in only one direction. Similar to the segment, we have an endpoint, but just one. And then it's going to pass through another point and go on forever. When we refer to our ray, we would have ray, and here the order does matter because we're starting at our endpoint A or initial point A and we're going through B. We could also write AB and put a ray above, keeping in mind that order does matter. Now you could reverse the order and write BA, but you also have to reverse the ray. So it starts at A and it goes through B. With two rays, we can create angles. When we talk about the vocabulary of angles, we have an initial side. So that's where we start. That's our starting ray. And we go in some direction. In this diagram, we're going up and around or counterclockwise. And then we stop at our other ray, which would be the terminal side. So some initial side, go some distance, and at a terminal side. This common point that the two rays have, they share the same endpoint, which we call a vertex. Now, in this case, if I wanted to refer to this angle, let's call this A. I can say that this is angle A, or I can use this little angle symbol and write A. But that's assuming that there's no confusion. And I'll show you what I mean. So let's say that I was going to start with the same initial side, And instead of going counterclockwise, I go down to some second ray. So now, when I say angle A, which angle am I talking about? It's not real clear. So in this case, we want to label some points that these rays are going through. On this upper angle, I'll just call this point B. The middle, call it C. The bottom one that I just drew, I'll call that D. So because there was confusion, I can't use just angle A. I have to be specific. So I could say angle, and here the vertex has to be the middle letter. So the upper angle, I could call that BAC or CAB. I could use the angle symbol, angle BAC, or angle CAB. The key here is that the vertex has to be the middle letter. Now in this particular angle, angle BAC, we're going up and around. So this is what we call a positive angle. It's going counterclockwise. Whenever you have an angle that's going up and around or in a counterclockwise direction, it will be a positive angle. Now the other angle that we drew is going clockwise, so that would be negative direction. Oftentimes it gets a little bit confusing to use three letters, or it's just tedious to use three letters to describe an angle. And in that case, we typically will just name the angle. So oftentimes you will see this Greek symbol, theta. So this upper angle, I'm just calling it theta. And then I need another name for the lower one, so I'm going to choose another lowercase Greek symbol, maybe alpha. So they have to be different letters. So again, commonly you will see Greek letters describing angles. So now I can just talk about angle theta or angle alpha. So let's move on to measurements of angles. And there are two ways that we measure angles. The first one that we're going to talk about is a degree measure. If you have some angle where you have an initial side and then you form your angle by going all the way around, and then your terminal side ends up being the same as your initial side, we say that we've gone a complete rotation. So a complete rotation around, where you start initial, go all the way around, and terminal is the same, would be a 360-degree angle. So other common angles that we'll see would be what we call an acute angle. So this is where the angle measurement is going to be between 0 degrees and 90 degrees. And then if you have an angle that's exactly 90 degrees, that's what we call our right angle. And here the right angle notation is this little box. So whenever you see the box in reference to an angle, you know it's a right angle. If our angle goes from 90 to 180 degrees, that's an obtuse angle. And then if you have an angle that's equal to 180 degrees, that would be what we call our straight angle. Some other language that may come up: complementary angles and supplementary angles. So when we say complementary angles, or angles that are complements of each other, that just means that if you were to sum them or add them, the total would be 90 degrees. When we talk about supplementary angles, or angles that are supplements of each other, if you were to sum or add them, it should equal 180 degrees. So if we look at this first diagram, this is an example of complementary angles. I clearly have a right angle, and let's just say that from the picture it looks like this would be maybe 45 degrees and 45 degrees. Add them up, I get a 90-degree angle. So they are complements of each other. In this second, I can see that I have a straight angle, and it's broken up into two angles. Maybe this is about 50 degrees. So the obtuse side would have to be 130 degrees. In example 1, we're going to find the measure of each angle. Don't go by the drawing, go by the numbers. Now I see that this is a right angle. So I know that these are going to be complementary angles. And since I know they're complementary angles, I know that if I take the two angles and add them up, I should get 90 degrees. So I'm going to leave off the degree symbol and take the first angle, which is x minus 6. And I'm going to add it to the second angle, which is 2x plus 18. That should equal to 90 degrees. I get 3x plus 12 is equal to 90 degrees. 3x is equal to 78. And then dividing by 3 should be 26. However, the question was to find the measure of each angle. So that just tells me what x is. One angle is x minus 6, so 26 minus 6 is 20, and it's going to be degrees. Since they're complementary, I can see that the other angle has to be 70 degrees. However, I'm going to go ahead and plug it in. Remember, that was 2 times x, which is 26, plus 18. I just want to double check my math. And that would be 52 plus 18 would give me the 70 degrees. These are the measurements of the two angles. Notice that there, if you were to look at the picture, you would think 45, 45. So don't go by the picture. That's just a generic set of complementary angles. Go by the algebra. So the upper one would be our 20 degree, lower one would be a 70 degree angle. Now that we've talked about a lot of vocabulary with the angles and so on, we're going to take these angles and we're going to put them into our XY coordinate system, or our Cartesian coordinate system, XY plane, however you want to call it. And once we do that, our goal will be to make sure that these angles are in what we call standard position. So when we talk about standard position, and if you look at these two angles below, these are angles that are in standard position. That just means the vertex is going to be at the origin. The initial side is on the positive x-axis. Let's look at this first diagram. So you see we have an initial side on the positive x-axis, vertex is at the origin, and then we just have a terminal side somewhere else. It doesn't matter where that terminal side is. To be in standard position, vertex at origin, initial side on the positive x-axis. And then we have another example in this second diagram, same thing. We have an initial side on the positive x-axis. Our angle goes around into quadrant 2, where we have our terminal side, vertex is at the origin. So it's just another example of an angle in standard position. But it doesn't have to go in the positive direction. Remember, we could also go around. So I'll look at this first diagram. If I were to go around in the other direction, I have another angle that's in standard position because initial side is at the positive x-axis, vertex is at the origin. It's just going in the negative direction, so it's still in standard position. There are special standard position angles, and I typically don't use this language, quadrantal angles. So the quadrantal angles are just angles that happen to fall on either the X or the Y axis. So if we look at this second diagram, if I have terminal or initial side, sorry, on the positive x-axis, vertex at the origin, and I was just going to go around to the y-axis and I would get this right angle. This is an example of a quadrantal angle. It's an angle in standard position where the terminal side is, in this case, on the y-axis. And there's going to be the common quadrantal angles, which would be at 90 degrees. And then if we kept going around, we would have 180 degrees. That would be our straight. If we keep going around, notice that now that we're in our XY coordinate system, things are broken up into four. So each quadrant is a distance, an angle distance of 90 degrees. So if I keep going around, I will have 270 degrees. That would be another common quadrantal angle. And then coming back to the beginning, this would be 360 degrees. Remember, we started at 0 degrees. So those are our common quadrantal angles. And then this last diagram here is just a cheat sheet for common positive angles, and we're only looking at one rotation. So if an angle happens to fall, and again, standard position, in quadrant 1, its measurement would be from 0 to 90 degrees. If the angle falls on the y-axis, 90 degrees, if we keep going around into quadrant 2, we will have an obtuse angle between 90 and 180 degrees. Keep going around to our straight angle, which is 180 degrees. That's quadrantal. And then in quadrant 3, our angles are going to measure from 180 to 270. Keep going around. Once we hit an angle of 270, it's another quadrantal angle. Quadrant 4 angles here would be measurement between 270 degrees to 360 degrees. And all the way around, it would be our 360 degrees, which again is another quadrantal angle. So just for reference and as a reminder, these are just positive measurements of angles with one maximum rotation. Again, reminding you angles can be negative and they can go around in the opposite direction. And that brings us to example 2, where we're going to sketch each angle. In part A, we want to draw a 150 degree angle. So going back, remember this is 0 degrees where we start at, and then we go to 90 degrees, 180 degrees, and I could see that 150 degrees would be in quadrant 2 between 90 and 180. And since this angle is closer, 150 is closer to 180 than it is to 90, again, I'm just sketching this. I would sketch it probably, oh, that's kind of off, but good enough. It's just a sketch. So typically we would put the angle measurement where we put our, and here I'm going to make it a positive angle so the arrow has to go positive. So usually we put the measurement where that little arrow is. It shows us what direction we're going in. However, I am going to label it at the end of the arrow because I'm going to label all of these angles A, B, C, and D on the same coordinate system. In B, we have an angle of 200. So if I went around further, I would have 270 degrees and a complete rotation of 360. So I can see that 200 is between 180 and 270. And it looks like it's closer to 180. Oh, my drawings are horrible. So we're going to go around, and this would be 200. C is negative 90 degrees. We're just going to be careful that we're going in the negative direction. And if we're going 90 degrees in the negative direction, we would end up here at this quadrantal angle. So this is 270 degrees, but it's also negative 90 degrees. And then if we look at D, D is already sketched because it's the quadrantal angle 270. So notice that the initial and terminal side for positive 270 degrees and a negative 90 degrees are the same. They have different angle measurements, but their initial and terminal sides are the same. They've just gone in different directions. And that's really important. Those are special angles. Those are what we call coterminal angles. So in coterminal angles, these are angles that differ by a factor of 360 degrees. So if you add or subtract multiples of 360 degrees, those angles would be what we call coterminal because they have the same initial side and the same terminal side. In these diagrams, we have two examples. In the first example, you see that we have this smaller angle, 60 degrees. So we've gone 60 degrees and stopped. And then this second angle, which is coterminal, starts in the standard position. It's going around one full rotation plus another 60 degrees. Terminal side is the same. So what we're saying here is that if you go 360 degrees plus the 60 degrees, that's going to equal to the 420 degrees. These are coterminal angles. They differ by 360. So if you can add or subtract multiples of 360 degrees, the angles are coterminal, same initial side, same terminal side. But it doesn't have to be one rotation. In this second example, the first angle that we're looking at is this angle of 110 degrees. So we've gone into quadrant 2. We have our terminal side. And then our second angle starts, same initial side, goes around one full rotation. So that's 360 degrees. Keeps going another full rotation. So that's another 360 degrees. And then goes 90 to 110 degrees. So if we add that all up, we get 830 degrees. So 830 degrees and 110 degrees are coterminal. They differ by 360. Again, in this case, I added 360 twice to get from 110 to 830 degrees. Same initial side, same terminal side. And we can go in the negative direction as well. We can go on forever and ever in both directions. Some language that you may see when you're going through the exercises in the textbook is similar to the language in example 3. In example 3, it says find the angle of least possible positive measure coterminal with each angle. So all that means is find a coterminal angle that's positive and as small as possible. In the event that an angle is negative, what you want to do is you want to add 360 until you reach a positive angle. In the event that the angle is positive, like is in part B, but really large, larger than 360, in that case, you're going to subtract 360 until you get to a small positive angle that's between 0 and 360. So let's look at example A. if I were to add 360 degrees, so remember that's the same as 360 minus 88, I would get 272 degrees. This is a positive angle. It is between 0 and 360, and I added 360 to the negative 88, so they're coterminal. So this is the angle least possible positive measure coterminal with negative 88 degrees. For 912 degrees, that's larger than 360. So what I'm going to do is I'm going to subtract 360 degrees and see if I get an angle between 0 and 360 that's positive. It turns out that I get 552. That's still larger than 360. So I'm going to subtract another 360, and I get 192. I would stop there because now I have a positive angle between 0 and 360 that is coterminal with 912 degrees. We've been talking about measurement in degrees, and we typically use degrees, and those are just units of measure, because it's something that we can all understand. If I said I was hiking and I was hiking up an incline of 30 degrees, we could all probably picture what that incline would look like. However, we don't actually do computations in degrees when we're looking at formulas. Think about something like a percent. If we were looking at a mixture problem and we're talking about percentages, if I said 50%, you would understand that to be half of the mixture. However, when I need to solve an equation using mixtures, I have to translate that percent to a decimal because my equation doesn't work with the percent measure. Same with degrees. Degrees are a special unit that we can picture, but we don't use them when we're looking at formulas. What we use is what we call a radian measure. When we say radian, it refers to the measure of an angle. So here, this is an angle measure. If I could write with my pen. And all that tells us is, okay, we're talking about an angle measure in real numbers, like decimals, when we go from percents to decimals. If you have the degree symbol, you're in degrees. If you have no symbol, you're in radians. When we talk about radians, what we're going to do is we're going to look at what we call a central angle. So a central angle is the angle that you see in this diagram below. A central angle is just an angle that's in standard form, and it intersects a circle. So where it intersects a circle, now in this diagram, this particular circle has some radius r. If the angle forms a length around the circle, and that's what we call our arc length. So if the arc length, that would be between the initial side and the terminal side of our angle, is equal to the radius of the circle. In this case, if they are the same, that is what we call 1 radian measure. And it's 1 because we're just taking the arc length, in this case it would be the radius, divided by the radius, that's equal to 1. So 1 radian is where the arc length and the radius of a circle are the same. However, if you're talking about any angle theta, and you want to figure out the radians, or the angle measurement, you would just look at the arc length, which we're going to use a different variable than r, because they could be different. The arc length, which we call s, and the radius of the circle that our angle is intersecting is r. So anytime you have the arc length divided by the radius, you get your angle measurement. However, remember this is in radians, this is not degrees. So when we do computations, oftentimes we have to convert from degrees to radians or radians to degrees. It depends on what the problem is. And it's a very simple conversion. The conversion from degrees to radians, all you have to do is multiply by pi over 180. If you're going from radians to degrees, then you flip it and you multiply by 180 degrees over pi. When you're working in radians, writing the word radians is optional. If there is no degree symbol, we assume it's in radians. So you can, or if you want, you can put the word radians or not. But if you're in radians, don't use that degree symbol. When you're in degrees, you have to put the degree symbol on. Radians, you can write the word radians or just leave it off. In example 4, we're going to convert from degrees to radians. We have 80 degrees. I'm going to ignore the degree symbol and multiply that by pi over 180 to convert. This would be 80 pi over 180, and don't forget to reduce. So 80 over 180 will be 8 over 18 divided by 2, 4 pi over 9. And since it's in radians, I don't have to write those units, but I will. So it's 4 pi over 9 radians, and what tells me is it's an angle measurement because of the radian units. If I have an angle measurement of a negative 150 degrees, again, I would just multiply that by pi over 180, ignore the degree symbol. The negative is still going to stay. I have 150 times pi over 180. And then I would reduce that. 15 over 18 divided by 3, 5 pi over 6. That is the exact answer in radians. If we want to convert from radians to degrees, we do the opposite. We would instead multiply by 180 degrees over pi. And here I'm adding the degree symbol. When I multiply, you can see the pi would cancel in this particular case. And I would get 1800 degrees over 3, which would give me 600 degrees. Again, when you're working in degrees, gotta have that degree symbol there, or else we'll assume it's in radians. In B, we have negative 3 pi over 4, so again, multiplying by 180 over pi, and we need to add our degree symbol here. It looks like still going to be negative. You know what, I'm going to reduce it first because I can see that 4 goes into 180 45 times. So 45 degrees times 3 would be a negative 135 degrees. So here we have some reference or cheat sheets, I guess, that you can use. The first is in table form and the second is circular. In this table, we're looking at some common angles that we use quite often. And here, notice that it's just positive angles from 0 to 360 degrees. So we're going to have our degrees, and then we'll look at the corresponding measurements in radians. So first we see an exact measurement in radians, so 0 degrees is 0 radians, and the approximation. And here the approximation is taken out to 4 decimal places. If we look at, say, 45 degrees, that's going to be in radians. The exact would be pi over 4. The decimal approximation would be 0.7854. Now you can use this for reference if you choose. I like the circular reference because you can kind of see where the angle position is as you go around this circle. So we start out at 0 degrees, which is 0 radians, and the circle has degree measures, radian measures, no approximation. These are exact values. As we go around, we hit 30 degrees, which is pi over 6, 45 degrees pi over 4, 60 degrees pi over 3, and so on. The next thing we're going to talk about is how we measure arc length and area of sectors. So remember, the arc length is just the distance along a circle, but it doesn't have to be all the way around the circle. It can just be a portion. So if we look at this circle here, whenever you have some central angle, and this would be our central angle theta. So if you have some central angle theta, and you have some circle of radius r that intersects this angle, you will have this corresponding arc length between the initial and terminal side of your central angle. So remember, we call that S. So the formula for finding the arc length is simply arc length S is equal to the radius times theta, but this is the important part. Theta has to be in radians to use this formula. Cannot be in degrees or the formula will not work. In example 6, we have a circle. It has a radius of 5.68 inches, so that's an exact measurement. It's not an approximation. And we're asked to find the arc length S. And here's some language you may see in your textbook. Find the length S of an arc intercepted by a central angle, theta, having the following measurements. So that's just find the arc length. You have a radius, given that angle, what is your arc length? In part A, notice there's no degree symbol, so I can assume that this is in radians. I don't need a conversion. I can go straight to my arc length. My arc length S is equal to the radius, which in this case is 5.68 inches. And I'm going to multiply that by theta, which is 3 pi over 5. Now remember, this is a measurement. It's a length. So the units are going to be inches because the radius is in inches. When I put that in my calculator, I'm going to put in 5.68 times 3 divided by 5. And it turns out to be an exact decimal 3.408. Pi is still there, inches. So I wanted to point this out, that this is an exact answer. Once I substitute for pi, maybe 3.14, or you use pi in your calculator, what you're going to get is an approximation. So if I did 3.408 times pi in my calculator, and I'll go out to 3 decimal places, it's 10.707 inches. So this is an approximation. Just be careful when you're doing assignments, whether they ask you to round the answer or give an exact answer. In part B, I can't use the arc length formula because my angle is in degrees. I have to convert it to radians first by multiplying by pi over 180 and dropping the degree symbol. That's going to be 110 over 180, or 11 over 18. So 11 pi over 18. And that's going to be my angle theta in radians. My arc length is going to be 5.68 times 11 pi over 18 inches. Now, in my calculator, when I put in 5.68 times 11, I get 62.48 pi over 18. If I divide by 18, I get a repeating decimal. So I'm going to stop here to be the exact solution. It's not really simplified though, because technically we shouldn't have decimals in a fraction, but I'm okay with that. It's exact. And then if I were to take 62.48 times pi and then divide it by 18, I get 10 point, round it to 3, so 905 inches. And then that would be an approximation. We talked about the arc length, the length along a circle. The next thing we're going to talk about is the area of a sector. So when we talk about the area of a sector, it's going to be, if this were a pie, it's that wedge or the piece of the pie. So we're going to have our central angle, and it's going to intersect a circle, and it's going to be the area within the central angle, bounded by the arc length. Again, when we use the formula for the area of a sector, we have to remember theta is in radians. And the area of a sector is similar to the area of a triangle. Triangle is 1/2 base times height. In this case, because our wedge is rounded where the arc length is, it's going to be 1/2 radius squared times theta. In example 7, we're going to find the area of the sector. Here the radius is 2 inches. So although you don't see the units in the diagram, it's in the word of the problem, so it's 2 inches. So we have to remember that area are units squared. So my final answer is going to be something inches squared. Here my angle is 65 degrees, so I'm going to have to take my angle theta first and multiply that by pi over 180 to convert it to radians. So we have 65 pi over 180, which should reduce to 13 pi over 18. No. Wait, no, 36. Is that right? 65 pi over 180 divide by 5, 1, 3 divide by 5, 3, 6. Yes, 13 pi over 6. And now my area of this sector is going to be 1/2 times the radius, which is 2 inches. I'll add the units on at the end, but it's radius squared, so it's 2 squared. And then we're going to multiply that by theta, which is 13 pi over 36. So don't forget the units here are inches squared. 1/2 times 4 would just be 2. So we get 2 times 13 pi over 36. That should give us 13 pi over, what's 36 divided by 2? 18. So 13 pi over 18 inches squared. That again would be our exact solution. If we needed to approximate that in a calculator, it would be 2 point, let's go 3 decimal places, 269 inches squared. The last topic in this section is going to be what we call angular and linear speed. When you think of the arc length, that's a distance along a circle. So that would be what we call a linear distance. But then we also have this idea of this angle theta going around our circle, and that would be our angular measurement. When we talk about speed, anytime we talk about speed, it's always some distance over time. So when we talk about angular speed, and here we're going to use this weird looking W, but it's not. It's a lowercase Greek symbol. This is actually lowercase omega. So we're going to use that omega to stand for angular speed. So when you think about angular speed, all you're doing is looking at the speed that an angle, theta, is changing over time. It's a very simple formula and it makes sense. You're looking at how the angle changes over time, so it's theta divided by time. Again, we have to be really careful because theta has to be in radians. When we look at linear speed, and it's that word v, this is another Greek symbol. This is the Greek symbol nu. It's a lowercase nu. Linear speed is simply the speed that an arc length s is changing over time. So since it's arc length over time, it makes sense that the formula is s over t. But remember, the formula for arc length is also r times theta. So when you're figuring out linear speed, you can also use, instead of s, r theta over t. It just depends on the information that you have. And now look at the theta over t. That's our angular speed. So we can actually take our theta over t and replace this with angular speed to get our final formula that we can use for linear speed, which is simply radius times angular speed. Again, theta is in radians. Now, I haven't assigned any angular speed or linear speed problems from our textbook, and that's because I'm not really impressed with the choice of exercises they have. They're very, very complicated. However, I am going to go over this example, and you can see that this is similar to things that you would see in your textbook. Oftentimes when we talk about speed, we're going to have to do a bunch of conversions. In example 8, we have the wheels of a skateboard have a diameter of 2.4 inches. So first thing I see is that they're talking about diameter. And in all of our formulas, we need a radius. So right away I can see that I need to compute the radius, which is half the diameter. So it's going to be 1.2 inches. So the wheels on a skateboard have a radius of 1.2 inches. Let's say the skateboarder is traveling downhill at 14 miles per hour. A, approximate the angular speed of the wheels in radians per second. Unfortunately, the speed that I was given is in miles per hour. So I see seconds and hours. Those units don't match. I'm going to have to do some conversions there. And also we have miles, but the radius is in terms of inches. So I have inches and miles. I'm going to have to do some conversions there as well. And then in part B, we're supposed to approximate the linear speed in inches per second. So once we find our angular speed, I think I'm going to use that last formula to find the linear speed. In part A, I need theta. Nowhere in the information that I was given is there a theta. So I'm going to actually have to go back, and this is often the case in these types of problems, and go back to my arc length formula, which is r times theta. Because I have r, and I actually have the arc length. It's that 14 miles per hour. The 14 miles is a distance. Imagine if you had a wheel on a bicycle and you took some bright red chalk and you rode the bicycle. you would get a line on the pavement. So that arc length around your tire is the same as a distance traveled. So we do have 14 miles. I do have the arc length, and I can use that to find theta. If I divide both sides of the equation by r, I have that theta is equal to the arc length over the radius. So I have arc length, I have radius, I have to just do some crazy conversions and I'll be okay because I know that the radius is 1.2 inches. So first of all, my arc length is going to be that 14 miles because that's the distance traveled, but we want inches, we don't want miles. So a common conversion is that for every mile, there's 5,280 feet. So each mile is 5,280 feet. So if I just multiply the 14 by 5,280, I get the length in feet. However, each foot is made up of 12 inches. So now if I take the amount of feet, multiply that by 12, I'm going to get inches. In my calculator, I get 8,87040 inches. That's the arc length. Now theta is going to be equal to that arc length, which is 8,87040 divided by the radius, which is 1.2 inches. Theta, so in a calculator, this is going to be 739,200 inches. Oops, not inches. Well, that doesn't help. Radians. Okay. So there's theta in radians. Now, all I need is the correct time. Our units here, going back to question A, it says approximate the angular speed of the wheels in radians. So we have theta in radians per second. This is miles per hour. So we have to go from hours to seconds. We have miles per hour, so we have 1 hour. There are 60 minutes in an hour. And then there are 60 seconds in a minute, which gives me 300 or 3600 seconds. Oh, that was a lot of converting. Now we can finally answer angular speed. We have our theta in radians. We have our time in seconds. So radians per second would simply be, angular speed is that weird W, 739,200. Remember, this is radians. Over 3600 seconds. Radians per second. Why don't we just approximate this? Because we get this long decimal. So I'm just going to write this to not even one decimal. I'm just going to write it as 205. And this would be radians per second. Well, that was a little crazy. However, part B is going to be easy because we have our angular speed, which means our linear speed, which is that word v. And we can use the exact angular speed, which was that 739,200 radians over 360, or you could use the approximation, seconds. And we're going to multiply this by our radius, which is 1.2 inches. And you could write that over 1 if you wish. So remember, we never really have to write the radians. When I put 739,200 times 1.2 divided by 3600, that's inches per second. And that would approximate to 246. If you would just use the 205 from part A, you would get the same. 246 inches per second. Again, a lot of conversions there. And I wasn't too impressed with the questions in the book. So wanted to go over this because we may see this later in this course when we talk about vectors. It may come up again. And that's it for this section.